Today we want to talk about the cycloalkanes, the fourth homologous series of the hydrocarbons. We have talked about the alkane, alkene, and alkynes, and we have talked about the naming of them, how we should name them, and we said that each one of them they have their specific general molecular formula. What was general molecular formula for each one of them? For the alkane, it was CnH 2n plus 2. For alkene, it was CnH2n. For alkyne, it was CnH2n minus 2. For example, if the alkane had 6 carbon, its molecular formula is C6H. 2 times 6 becomes 12, plus 2 becomes 14. And the alkene with 6 carbon, it has 6 times 2, 12 hydrogen. And alkyne with 6 carbon, it has 6 times 2, 12, minus 2, 10 hydrogen. So from the general molecular formula, we can guess if we have alkane, alkene, or alkyne for the hydrocarbons. Another group of the hydrocarbons are cycloalkane. So I want to talk about the cycloalkane. The name suggests two important points about their structure. The cyclo tells us that we have a ring structure of the carbon, and alkane, A-N-E, suggests that we have only carbon single bond carbon. Okay? So the famous example for the cycloalkane is cyclohexane. 6 carbons forms a ring member. So I showed the structure of the cyclohexane: 1, 2, 3, 4, 5, 6. So here you can see 6 carbons are joined to each other to form a ring structure. So how many hydrogen I have to put for each carbon?
2 for each carbon.
Yeah, so each carbon has already 2 bonds. So 2 valence electron remains for them. They must be shared with the hydrogen. So each one of these carbon shares electron with 2 hydrogens. So now the structure is complete. Okay. What is the molecular formula for this structure? How many carbon do we have here?
6 carbons.
6 carbon, and the hydrogen?
12.
12. So what would be the general formula for this cycloalkane?
Always CnH2n.
Yeah, if you have n carbon, the number of hydrogen is 2n. So you can see their general formula is like the alkene. Okay. So we can say C6H12, the hexene, and C6H12 cyclohexane, this compound is called cyclohexane. They are isomers of each other. They have same molecular formula, but their structure is different. The alkene is a straight chain hydrocarbon. Cyclohexane or cycloalkane, they are ring structure of the hydrocarbons. So alkene and cyclohexane, they have same molecular formula, same general molecular formula, and they are isomers of each other. But as you know, we don't show the bond between the carbon and hydrogen in the condensed format. So the condensed format of this structure would be like this. I draw the condensed format here. CH2, 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 CH2. This one is also cyclohexane, but it's a condensed format of cyclohexane. Again, we can even not show the carbons here and hydrogen. So sometimes we can draw just a hexagon, and this is cyclohexane. This is called a skeleton structure. Okay, so this is a skeleton structure. In a skeleton structure, at each corner you have carbon. So here I have one carbon, 2, 3, 4, 5, 6. So it suggests that I have 6 carbon, and each carbon has 2 bonds. This is one bond, this is the second bond. So we know that there must be 2 hydrogens. So we know what we have here is CH2 because it's the corner. So we have the carbon. That carbon bonds 2 single bonds with the 2 other carbon as we have here. So we must have 2 hydrogen for here. So this is the situation for any corner. So look at this corner that we have here. It has 2 single bonds, one with the carbon at the top, one with the carbon at the left side. So exactly same as the carbon that you have here. So we know that there must be 2 other hydrogens. So we can understand that at this corner we have CH2. And in the most of the textbooks, you can see the skeleton structure for the cyclo compound, for the cyclo alkanes. So I want to draw another member of the cycloalkane, and you tell me what is the name of this one. How many carbon do I have here in this structure?
5.
I have 5 carbon. One is here, 2, 3, 4, 5 carbons. And how many hydrogens?
10.
10 hydrogens, okay, twice as the number of the carbon. So I know that at each corner I have a carbon, and that carbon is bonded to 2 other carbon by a single bond, as you can see here. So they need 2 bonds with the hydrogen to become complete. So I know that at each corner I have CH2. CH2. And always in the cycloalkane, the members inside the ring is CH2. If you don't have the branch, the member is CH2. So this one is, what is the name?
Cyclopentane.
Exactly, it's cyclopentane. Okay. What about this one? What is the molecular formula?
C4H8.
C4H8. We have 8 corners here. It means we have 8 carbon, and each carbon has 2 single bonds, so they need 2 hydrogen. So if you put 2 hydrogen for each one of them, totally you will have 8 hydrogen. What is the name?
Cyclobutane.
Exactly, cyclobutane. Okay, what is the smallest member of this homologous series? How many carbons are in the smallest member? Okay, so we can have less carbon than 4. We can have this structure. How many carbon do we have? We have 3 carbons.
And 6.
6 hydrogen. So this one is cyclopropane.
Propane.
Okay. The structure is CH2, bonded to CH2, bonded to another CH2, and they bond to each other. So this is cyclopropane. But we cannot have a cycloalkane with 2 carbons, because if there is only 2 carbons, they cannot form the ring structure. Okay, so we don't have C2H4. So the smallest member for the cycloalkane has 3 carbons. So this is the smallest member of the cycloalkane. So this is another group of the hydrocarbons which they form the ring structure, and you have them here on page 684. So at the top of the page you have the cyclopentane. It shows both the condensed structure and the skeleton structure for that one, and the definition of the cycloalkanes is given at the top of the page. Cycloalkanes are alkanes in which the carbon atoms are arranged in a ring or cyclic structure. So they must have the ring structure, and the general formula for the cycloalkanes, this is the general formula for the non-cyclic alkanes. For the cycloalkanes, you have 2 less carbons. So the general formula for the cycloalkane is CnH2n, same as alkenes. Okay. Now I want to come back to the alkane to talk a little bit about the properties of the alkane. Okay. So the properties of the alkanes are related to the length of the carbon chain. So the only difference between the member of the alkane homologous series is the length of the carbon chain. The smallest member is methane. It has only 1 carbon. The next member is ethane. It has 2 carbon. The next member is propane, 3 carbon, 4 carbon, and so on. So one more time, I draw them here. So the first member is methane, is CH3. The next member is, sorry, CH4. The next member is CH3, CH3. The next member is CH3, CH2, CH3. So you can see the only difference is in the length of the hydrocarbon chain, and for each one of them they have 1 or more extra CH2 in the chain, and so on. Okay, these molecules are non-polar because the difference between the carbon and hydrogen, difference in electronegativities of carbon and hydrogen is small. So they have very small dipoles in their bond, but the arrangement of those dipoles is in the way that they cancel out each other. So these molecules are non-polar molecules. So the alkane, or generally hydrocarbons like alkene and alkyne, they are non-polar molecules. So if they are non-polar, what is the force of attraction between their molecules? Who remembers the intermolecular forces, the forces that we have between the molecules?
So in molecule which is non-polar, the only force is the London dispersion forces.
Yeah, for the non-polar molecules, the only force which is available between the molecule is the London dispersion forces. But generally, the intermolecular forces are dipole-dipole attraction, they are hydrogen bonding, and
Dipole-induced dipole.
Dipole-induced dipole in special cases when you mix a polar and non-polar molecule, and the London dispersion forces which are available between all of the molecules. But for the non-polar molecules, the only force of the attraction is London dispersion force. Okay, so the strength of the London dispersion force depends on what?
How massive the molecule is.
How massive is the molecule? So if the molecule becomes more massive, it means it contains more electron, and the chance of formation temporary dipole increases. So it means the London dispersion force becomes stronger. So that's why here, by increasing the number of the carbons in the hydrocarbons, the molecule become more massive and the London dispersion force increases. So the boiling point and melting point of this compound increases by the number of the carbon. This is very important trend that you have in each of these hydrocarbon homologous series. So here we are talking about the alkane. So we can say in the alkane, by increasing the number of the carbon, the molecule becomes bigger and more massive. So the strength of the London dispersion force increases. So that's why the boiling point and the melting point of them are increases. So the first member, the methane, which is the smallest, it has lowest melting point than the boiling point. Okay, actually the first four alkanes, methane, ethane, propane, and butane, their melting point and boiling point are low, below the room temperature, so they are gas. But for C5, H12, and upward, the London dispersion force is increasing. Their boiling point is higher than the previous hydrocarbons. So they are liquid at room temperature. And when the number of the carbon becomes very big, the hydrocarbons become solid. Here in your book, in this table, the boiling point of these alkanes are given. So you can see by increasing the number of the carbon here, by increasing the number of the carbon, their boiling point are increases. Suppose the room temperature is 25 degrees centigrade. You can see that for the first two or for first four alkane, their boiling point are below the room temperature. It means the room temperature is high enough to evaporate them, so they are in the gas format. But for the next hydrocarbons up to 10 carbon, the boiling points are given here. The boiling point is above the room temperature, so they can be either solid or liquid. So to identify if they are liquid or solid, you have to also look at their melting point. Same as the boiling point, by increasing the number of the carbon, their melting point increases. For the carbon number 5 up to carbon number 10, their melting point are below the room temperatures. Okay, so they become liquid, but when the number of the carbon becomes very weak, their melting point also increases and it becomes above the room temperature, so they remain solid. So these trends are very important. You must know that by increasing number of the carbon, their boiling point and melting point increases. And for the first four hydrocarbon, you must know that they are gas because the room temperature is above their boiling point. Okay, so all of these alkanes are available in the crude oil that we extract from underground. But the mixture of all of them are useless. So we have to find a way to separate them from each other. They have different boiling points, so we can use the boiling point differences to separate them from each other. And that's what is done in the refinery column, in the petrochemical power plants. It says the petroleum is a complex mixture of the different hydrocarbons that varies greatly in composition. So the different composition or different number of the carbons are available in petroleum. So we have to separate them, and we use fractional distillation for separating them. Fractional distillation is a technique that we use the difference in the boiling point of the mixture, of the component of the mixture, to separate them from each other. And they do this one in the fractional column that you can see here on the right side of the page. This is the fractional distillation column. Okay. So you can see in this column, you have different temperature. At the bottom of the fractioning column, the temperature is high, 600 degrees. But as you go above the column, the temperature drops. For example, here is 270, 170, 120, 70, and 20 degrees. So as you go up, the temperature decreases. They exert the crude oil from here at the bottom. The crude oil composed of all of these alkanes from carbon number 1 to up to carbon number 17 and above that. So when you exert the hydrocarbons here, because the temperature is high here, 600 degrees, this temperature is above the boiling point of most of them. All of them evaporates. All of them converts to the gas. When they convert to the gas, they goes up in the column. So they have some path and some ways to go up in the column. But as they are going up in the column, the temperature drops. So suppose you reach to here, all of them comes to the here, the temperature would be around 450 degrees here. So what happened at that point? No, some of the hydrocarbons liquefy because the temperature is below their boiling point. 450 degrees is below their boiling point. So what happens? Some of them, they liquefy at this point. When they liquefy, they can come out from the column at this point. But the rest of them, the temperature is still above their boiling point. So they are still in the gas form. They remain in the gas form, and again, they go up in the column. So what happened when they go one level up? Again, the temperature drops from 450 degrees to 270. So now, again, the temperature is below the boiling point for some of them. So they liquefy here. Okay. They liquefy and they come out from this part. Okay. But the temperature is hot enough for some of them to remain in the gas. Again, they move up in the column. And again, when the temperature drops below their boiling point, what happens? They liquefy and they come out from the path that they have. For example, they come out from here. So as you are going up the column, what happens? You are separating the hydrocarbons from each other. So, and finally, some of them, they go out at the top of the column as a gas. And they are carbon number 1 to 14, from methane to butane, because their boiling point is below the room temperature. So they remain the gas all the path and they comes out from top of the column. So you can see by using the fractioning column, we can separate these hydrocarbons based on their boiling points. But at the end, some of the hydrocarbons, they have very high boiling points in a way that this 600 degrees is not enough to evaporate them. So what happened? They don't evaporate, and they remains in the liquid format. So what happened when they become liquid? They come out from the bottom of the column. You can see the number of the carbons and their name and their range in the boiling point. Okay. For example, the carbon, which their size is between 4 and 12, they remains liquid up to 200 degrees. So if the temperature is above 200 degrees, they become gas and they go up here in the column at the right side. Okay. But when the temperature drops below 200 degrees, they liquefy and they come out. For the next range of the molecules from carbon 10 and carbon 14, the boiling point is 180 to 290. So what happened? They come out at the lower part because the temperature is low here at the top and the temperature is high here. So for the first 4 carbons, they go farther in the column, and then when the temperature is below 200 degrees, they come out. For the next group, they go up in the column, but at the lower point, their temperature drops below their boiling point and they come out from there. So you can separate any group based on their boiling point in the column. So what is important, you must know which molecules comes out or liquefy at the bottom of the column, which one goes farther in the column and comes out. Okay, the hydrocarbons, which are small, they have lower boiling point, so they go farther in the column and they are separated at the top of the column. And the hydrocarbons, which are big, they have high boiling point and they go a little bit up in the column and they come out at the bottom of the column. And for some of them, like for example above carbon 36, their temperature, their boiling point is such high that we cannot evaporate them. We just can liquefy them and it comes out at the bottom of the column. We use them as an asphalt. Okay, so each group of these alkane, they have their specific usage. So you can see here, for example, from carbon 1 to carbon 4, we use them for the cooking, we use them for warming our houses. From carbon number 1 to carbon number 9, we call them naphtha, and we usually use them in the petrochemical products. From carbon number 5 to carbon number 10, we call them gasoline. We use them in the car as a fuel. Okay. From carbon number 10 to carbon number 16, they call kerosene. They are the airplane fuels. From carbon number 14 to 20, they are called diesel, and we use them as a diesel fuel. From carbon number 20 to carbon number 50, we use them as a lubricants, like the waxes, polishes, and these stuffs. Okay. And the alkane with 20 to 70 hydrocarbons, we usually they use as a fuel in the boilers. And when the number of the carbon is very high, they use as a bitumen for asphalting the roads. So they have different usage based on the number of the carbon that you have in the molecule. But I want to talk about their isomers. Okay, so look at this one, the two molecules that we have here. As we said, when we have the double bond, we can have geometric isomers. So we have to look at the groups which are connected to the double bond. Okay. Here to the carbon at the left, hydrogen and methyl is connected. To the carbon at the right, also hydrogen and methyl is connected. But here the methyls are at the same side of the molecule. The hydrogen are at the same side as well. For the molecule which is written at the right, the methyl groups are at the opposite side. The hydrogens are at opposite side. So they have different geometry. And based on that one, if they are at the same side, we say they are cis. If they are in the opposite side, we call them trans. So if in the exam, the molecule which is given to you is the alkene, and they show their arrangement like here, you have to also mention if there are cis or trans isomers based on the groups which are bounded to double bond. Okay, so they are cis 2 butene, trans 2 butene. But why there are 2 butenes? Okay, so we have to find the longest chain, no matter how it's drawn. So the longest chain is this one. You have 4 carbons here, and you have to number the longest chain. So this is carbon number 1, carbon number 2, carbon number 3, carbon number 4. You don't have any branch. These are hydrogens. Don't confuse it with the branch. The hydrogen is not branch. So you have a straight chain alkene with the 4 carbon, and the double bond is in the second position. So you have 2 butene. What about the carbon which is written at the right side? Again, this is the longest chain. This is the longest chain. You don't have any branch. Number it 1, 2, 3, 4. So we have 4 carbons here. The double bond is on carbon number 2, so this one is also 2-butene as well. So the only difference is that the first one is the cis isomer, the next one is trans isomer. But look at the molecules that we have here. The longest chain is this one. It has 3 carbons. So this one is propene. And because for the propene, the double bond is always in the first position, we don't write 1 propene. But is there cis or trans isomers for propene or not? So look at the propene molecule. Look what is bonded to these carbons. The 2 carbons are very important. The carbon at the left, 2 same groups are bonded to that one. When 2 same groups are bonded to the carbon, then we don't have cis or trans isomers. We have just one arrangement. So this is the only propene. So for the propene, we don't have cis or trans. Okay? But for 2-butene, we have cis or trans isomers. What about 1-butene? Do we have cis and trans isomers for the 1-butene? Let's draw the 1-butene molecule here. Okay, so this is 1-butene. It's CH2, double bond, CH, CH2, CH3. So you have to look at the carbons which contains the double bond. So the carbon at the left side, it has 2 hydrogen, then double bond. The carbon at the right, what group is connected to the carbon at the right? 1 hydrogen is connected to that and 1 ethyl group. So it has 1 hydrogen and 1 ethyl group, CH2, CH3. So you can see for the carbon at the left side, 2 identical group is bonded to that. So when the 2 same group is bonded to either of these carbons at the 2 sides of the double bond, then you don't have cis or trans isomers. Okay, so for 1-butene, we don't have cis or trans. But for the 2-butenes, which the 2 different groups are bonded to each of these carbon at the 2 sides of the double bond, then we have the cis and trans isomers. Let's go to some examples of the alkene. On page 693, 2 examples of the alkene is given, which you can see in your daily life. The first one is shown here. It is farnesene. The farnesene is an example of the alkene. So this structure of farnesene is given here. You can see that you have a double bond in the molecules. Lot of double bonds. So they are alkene. This is a long chain alkene. So it is solid at room temperature because its London dispersion force is strong. And the farnesene, you can find it on the skin of the apple. If you take a knife and you scratch the skin carefully, you can see some white wax is coming out. That is the farnesene. It is a natural wax. Okay, so in all of the apples, you have these natural wax, which we call it farnesene. Another example for the alkene is ethene, CH2 double bond CH2. Okay. CH2 double bond CH2. The ethene is a plant hormone. The fruits usually produce the ethene. The common name for the ethene is ethylene. Ethylene is used for the fruit ripening. So if you have tomato, which is green, if you put it inside the box or you pile it on each other, because they produce the ethene, this ethene gas acts as a hormone and it triggers fruit ripening. So these are 2 examples of the alkene that you can see around you. Also, some of the fruits, if they want to transfer from one country to another country, because it's usually take a long time for the transportation, they have to cut the fruit from the tree when it is not ripened. Okay, so when it reached to its destination, usually they expose the ethylene gas to that fruit, and then the fruits ripen and is ready to be in the market. Let's go to the alkyne. The famous example of the alkyne is ethine, that you can see its structure here, CH triple bond CH. Okay? The common name for ethine is acetylene. Okay? So don't confuse the common name. The common name contains ENE, but the acetylene is ethine. Okay, so this ENE doesn't mean the double bond. Okay, so the acetylene is another name for the ethine, that is the common name actually for the ethine. The ethine is used in the welding torches. Okay, as you can see here, when the ethine mixes with the oxygen, and when we burn this mixture, they produce a lot of heat, and that heat, intense heat, is used in the welding torches. So we use the ethine in the welding torches, and the mixture of the ethine and oxygen is called oxyacetylene. So the oxyacetylene torches are the torches that they use mixture of the oxygen and ethine for welding.